Right, this lecture is on controllability and observability, and it's based around some state space equations. X dot is x is bu, y equals cx. First of all, we'll just look at the definitions, and then we'll look at their meaning and how to compute them. So, a system is said to be controllable if at a time t0, that's the initial time, if there exists a finite time sequence t1, which is greater than t0, such that for any initial conditions x0 and any t1 or x1, there exists an input which will transfer the state from the initial state x0 to the state x1 at time t1. So it means that you can control, this is why it's called controllability, because you can control the system to go from some initial condition, some initial state, to some other prescribed state that you want it to go to. So that means that you've been able to control it to go from A to B. And that's the definition then of controllability. The second condition is observability. So controllability is about controlling something. Observability is more about seeing something. So a system is said to be completely observable at any time t0 if there exists a finite time t1 greater than t0, such that for any x of t0 and time t0, the knowledge of the input sequence and the output sequence over that time interval is sufficient to determine the initial state. Otherwise, the system is said to be unobservable. This is saying if you know where you are now, you know what sequence you've used from some time in the past to now, if you can map back to where the initial state is perfectly, then that system is defined as being observable. So it's almost like, but this is more based on what you can see. So now there's a formal definition now to work out the controllability of a system. So if we've got some system x dot as x is bu, we can work out a matrix now, which is defined as b, a squared b down to a to the n minus 1b. This is a matrix called the controllability matrix. And if this matrix is a full rank, then the system is said to be controllable. Similarly, for observability, if we've got again the system x dot is x plus bu, y equals cx, if we now work out another matrix which is c, ca to the n minus 1, so the a comes in at the back end here, and we transpose that again from this matrix. It's called the controllability matrix, and if this matrix is a full rank, then the system is said to be fully observable. So let's just look at what this term rank means. So the main thing about working out a rank is that if we're given a large number of linear equations, we need to count the number of essentially different equations. So imagine you've got, like, say, 5 equations. If those 5 equations are linearly independent, you can solve them. If you've got 5 equations and say 2 of them are the same, then sometimes you can't solve them. So this comes out as in a matrix case. If you look at this matrix here, this is the rank of the matrix is defined by its size almost, the maximum rank. So this is a 3 by 3 matrix, and it's actually got rank 3. Here's another example. We'll come back to why in a moment. If we look at this little matrix here, again it's a 3 by 3, but this time notice that this row and this row are linearly dependent because one's 2 times the other. So what you could say is that this matrix now, because this is linearly dependent with this one, this has only got rank 2, because there's only 2. If you think of these as representing, say, linearly independent equations, and you're trying to solve 3 equations for 3 unknowns, then in this case there are 3 linearly independent equations, so you could solve them, but in this case 2 of the equations are linearly dependent, and so you couldn't solve them. Now way of thinking about rank. Another way of thinking about rank is if we go back to our little example here, this determinant is non-zero. Whereas this determinant, because the two lines are linearly dependent, any matrix with two rows or two columns linearly dependent will have a zero determinant. So this is a nice little check now, quick check for checking the rank of a matrix. So here we have a 3 by 3, its determinant is minus 79, and so we can say it's got rank 3. Here now we've got the same one we had before. These are the linearly dependent ones, and if we work out the determinant of this, it comes out as 0. So a nice check for checking out the rank of a matrix is to see if its determinant is non-zero. If its determinant is non-zero, it means that the matrix is invertible and it has full rank. If the determinant is 0, it means that the matrix is not a full rank and it's not invertible. And this particular one, if you look at that 2 by 2 there, 1 times 3 minus 1 times 2, so that's got a determinant of 1, which is non-zero. So this has got a rank 2. So that particular matrix would have rank 2. If we had 2, 3, 4 there as well, then when we worked out any sort of determinant, it would also come out 0. And the biggest you could get would be 1, because there'd only be one linearly independent equation there. So let's have a look now at some sort of issues to do with working out now the observability matrix. There's two matrices to compute, observability matrix and controllability matrix. Now the observability matrix is easier to work out than the controllability matrix from a mathematical point of view. If we look at the definition of the output of a system, x dot equals x plus pu, y equals cx, with no input u, just some non-zero initial condition, then y of t is c e a to the t x of 0. So we could now the system will be observable if all of its derivatives are observable. So we could work out now, if we worked out this thing here, we could put t as 0, so e to the 8t is I, so it just becomes c times x of 0. If we work out the first derivative, if we differentiate e to the at, we get a e to the at. So differential of c e to the at is in fact ca e to the at. And we've put t as 0, this comes out as ca times x of 0. If we do the second one, we get ca squared x of 0. And if we went to do the nth one, it would come out as, or the kth one, say, it would come out as a k x of 0. So now, in order for the system to be observable, we have to have n of these have to have n non-zero values. So if we collect these up now into a matrix, we could build them up into an nth. So we got the c, that gives us 1, so that we don't need to go all the way to n, we can go to n minus 1. So ca squared down to ca n to the minus 1 times e to the at is 0, implying now that if the rank of this is equal to n, then the system is fully observable. So this gives us our observability test. ca squared all the way, form that matrix. If its rank is n, then the system is observable. Now, to do the controllability one is a little bit more tricky. So there's a little trick we can play. We consider some state space equations, x dot x y equals cx. We could consider an alternative system, which is the transposed system. So this will be some new state will be a transposed x plus c transposed u, and y will be b transposed x. So we've transposed the system now. So the b has become c transposed, the c has become b transposed, and the A matrix is A transposed. If we work out the transfer function of this, it comes out as in this, because now it's, instead of being c into si minus a to minus 1b, it can be transposed si A transpose minus 1 times c. And we can then work out the determinant of the original system, and the determinant of this, and because the eigenvalues of A are the same as the eigenvalues of A transpose, we can conclude that the poles of both systems are identical. If we look at the zeros are given by C into the adjoint of Si minus A times B, and for the transpose system, this becomes B transpose adjoint of Si minus A transpose C transposed. Now if we transpose this, we get this, and therefore we can say that the zeros of these two systems are the same as well. So an interesting property now is that the transpose system can be used in some situations, and it has exactly the same properties as the original system. And we're going to use this in 2 or 3 situations. So when we come down now to doing the controllability matrix, if we take our transposed system and work out now the observability matrix, it becomes B transpose A transposed, all the way down to B transpose A to the n minus 1 transposed. If we transpose this matrix, we get this matrix here, which is in fact the controllability matrix. So the proof, if you like, for the controllability matrix, this is an easy little way of proving it by using the transpose system. You can have a look at the proof for there's no alternative proof for the controllability matrix, but it's incredibly hard to follow. So let's look at an example now. Here's some transfer function, and one of the things about transfer functions in this format is you can't tell if you've got a pole zero cancellation, but in fact if we factorize this out, we notice we've got a pole zero cancellation. So if we work out the A, B and C for this system here, this is the A, B and C, we've put it into companion form, so it's like that number with negative sign, that number with negative sign, that number with negative sign, 0, 0, 1, and then these numbers here are those numbers there in reverse, so it says 1, it's 2, 3, 1, 2, 3, 1. That's our state space representation now for this system that's got a pole zero cancellation. Now if we work out now C, CA and CA squared, this is what we get here, and if we work out the determinant of this, it comes to 0. So this is a nice interpretation now of the observability and controllability. What it's really telling us is we've got a pole zero cancellation in our transfer function, and MATLAB has a nice command for doing this. If you know what the A is and what the C is, if you type in OBSV AC, it'll work out this observability matrix for you, so it'll save you all the time of working this out. Similarly, if we've got the same system here, and we've got the ABC, we could work out the observability matrix. And in this time, the determinant comes out as 1, indicating that the system is controllable, but it's not observable. So in state space systems, we really need it to be both controllable and observable for us to be able to do a full design. So but observability and controllability don't necessarily go, one doesn't imply the other one. But we've got, in this particular case, going back to this example here, we've got a pole zero cancellation in the system, which is we would like to know about really, and we can find this out by working out the observability matrix, controllability matrix. If either of those come down to 0, then we can conclude that it's got a pole zero cancellation. An alternative way of doing this is just to factorize this and look for the pole zero cancellation as well. And again, if we've got the A and the B, we can work out the controllability matrix through CTRB-AB as a MATLAB command. And then we could work out the determinant of this thing. And if either of the determinants are 0, then we would conclude that the system had a pole zero cancellation. And when we're designing some types of controllers, like pole placement controllers or observers, it's important that we don't have a pole zero cancellation in our transfer function. So we need to make sure that our control system that we're playing with is both observable and controllable. So we would have to work out the observability condition and the controllability condition to make sure that everything was fine.
Right, good evening. Today's lecture is on controllability and pole placement. And one of the issues that we can have with pole placement is that if we try and place a set of poles in a control system where there's a pole zero cancellation, in other words, there's an uncontrollable mode in the system, the pole placement algorithm doesn't work. So before we can carry out pole placement, we need to check the controllability of the system. So what we're going to do in this lecture is check the controllability of the system. Then we're going to discover that it's not controllable. We're then going to remove a pole and zero from the system to come up with a controllable system, for which we're then going to design a pole placement controller. So our first thing to look at is to look at the controllability of this, and in order to compute this we need to do a number of things. We need to produce some set of state space equations. Of this sort of format for this system, and the best format, the simplest one, is the companion form. So we'll obtain a set of companion form state space equations for the system, and then we can compute the controllability matrix. The controllability matrix is going to be given by C, CA, CA squared, and CA cubed. And the reason it's a cubic is because it's a fourth order system, so therefore there's going to be 4 lines to this matrix, which is CA to the 0, CA to the 1, CA to the 2, CA to the 3. And if the system is uncontrollable, we can show if the determinant of this matrix is equal to 0, then this system is in fact uncontrollable and unobservable. So this is going to be our little calculation, and the first thing we're going to do now is to compute some state space equations, and then we're going to compute this matrix here, and then hopefully show the determinant 0. So we can do this routinely in companion form. The first thing we do is fourth order system, so it's going to be 4 states. So we start on this side, so we get x1 dot, x2 dot, x3 dot, x4 dot, and we'll have a 4 by 4 matrix here, times x1, x2, x3, and x4, plus another matrix with the input in u. We'll have an output matrix y given by x1, x2, x3, x4. So this is now we can write the system in companion form. So this is fairly straightforward. We're in 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1. So we fill in the whole top with zeros, put a 1 down there, put a set of 1s, not on the main diagonal, but 1 off, and then these numbers here are these numbers here in reverse order with negative signs. So it's going to be minus 72, minus 126, minus 67, and minus 14. And these numbers here are those numbers there in reverse order. So it's going to be 12, 18, 6, and 0. So this now is our state space representation of our transfer function. So the next thing we have to do now is to compute the controllability matrix, or in this case observability matrix. So we can write down C first. That's going to be 12, 18, 6, 0. That's the C. Now what we've got to do is multiply the C by the A. So that means we're going to have to multiply this matrix, this vector or array, by this matrix. So we could represent that as 12, 18, 6, 0, and that'll be into a 4 by 4 matrix here. Which is going to be 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, minus 72, minus 126, minus 14, sorry, minus 67 even, minus 67 and minus 14. Now, we'll just need a bit of space for this, so we're going to rub this bit out here and generate ourselves a bit of space. And so we're going to work out, first of all, the observability matrix given by C, CA, CA squared, CA cubed. So that's what we're going to have to compute. So let's start off with the C. That's relatively straightforward. Let's put in 12, 18, 6, 0. So there's our first part of our matrix. We then multiply the 12, 18 and 6, 0 into this matrix. So we get this multiplies into this multiplies into this, that multiplies into that, and that multiplies into that. So it's rows into columns. And this will come out as 0, 12, 18, 6. So this now represents C, this represents CA. So to get CA squared, we could multiply CA by A and it would give us CA squared. So if we change now this one here to 0, 12, 18, 6, this is CA, so CA times A gives us CA squared. This one's slightly more bigger numbers here, minus 432, minus 756, minus 390, and minus 66. This now represents CA squared. So if we now remove this part here, and again replace this now with CA squared, which is minus 432, minus 756, minus 390, and minus 66. Multiply this by this, then we'll end up with CA cubed. So these are quite large numbers. 4752, 7884, 3666, and 534. So this now gives us our observability matrix, and what we're looking to show now is that the determinant of this is 0. So this is quite a tricky determinant. It's going to be 12 into that 3 by 3 minus 18 into the 3 by 3, which we get by removing that line and that line, and it's going to be plus minus plus a 6 times a 3 by 3 matrix formed about there with that one as the 3 by 3. So that's going to give us 3 by 3 determinants to compute, and if we add those up, we'll find that the determinant of this is in fact 0. And this now shows that the system has an unobservable pole. Now, routinely in an exam, this would be quite a tricky calculation to do, and this calculation would be quite tricky as well. But given that you might not be in an examination and you might have MATLAB available to you, it's possible to write some little MATLAB code which might help you with this. So let's just briefly look at that as well, shall we? So we could put C, put open square brackets, that's going to be 12, 18, 60. And we could put A equal to, and then this is going to be the A matrix here, so it's going to be, I'm getting a semicolon there for a new line, and it's going to be we have to have spaces in between these numbers. That would put in our A, C and A. So then it'd be possible then to compute C times A in MATLAB. Or you could compute C times A and C times A times A times A. And this would work out then, C times A would give you the second line, CA squared would give you the third line, CA cubed would give you the fourth line. And then you could formulate that then into a matrix, as we had there a minute ago. And once you've got that matrix, let's say that matrix was called some matrix X, you could just work out determinant of X. And that should, with a bit of luck, come out as 0. So that's an alternative little trick that you can play if you happen to have MATLAB handy on any particular time. So, what that's shown us is that the system now, because the determinant came out as 0, it's shown us that the system has a pole zero cancellation. Now, we might be able to work out where the pole zero cancellation is, but this is not always straightforward, because it would involve factorising these two polynomials. Again, if we had MATLAB available, I guess we could factorise this just by putting, say, A equals 6, 18, 12, and then simply typing in roots of A. And that would factorise that, and you could do the same thing to factorise this one. So you could work out what the roots were quite quickly. If you hadn't got MATLAB available, say it was an exam question, something like that, it might tell you that there's a pole zero cancellation at, say, s plus 1 equals 0. So in this particular case, there is a pole zero cancellation at s plus 1 equals 0. So what we have to do now is extract a pole at s plus 1 from this expression and from this expression. So it's going to give us 6s squared plus 18s plus 12. And we do a long division now. I've done that a little bit too high up. Just rub that out. We've got 6s squared, 18s plus 12, and we divide this by s plus 1. So this is going to go into this 6s. That's going to give us 6s squared plus 6s. Change the signs in the bottom line add. Give us 12s plus 12, and that's plus 6, or even plus 12. That will give us 12s plus 12. So, and then this we could factorise into 6s plus 2. So the top line can be factorised into 6s plus 1, s plus 2. So we've taken that one there, factorised it like this, and then we can have another go now at doing a long division on this one. So get s to the fourth, 14s cubed, 67s squared, 6s plus 72, and divide this one now by s plus 1, so it's going to be 14s squared, or it's going to be just s cubed actually. S cubed, that's going to be s cubed plus s squared, so change the signs and add. So s to the 4 plus s cubed. When you subtract these, we end up with 13s cubed plus 67s squared. S into 13s squared goes plus 13s squared. So 13s squared times that gives us the 13s cubed. And here we have 13s squared. Subtract these two, these disappear. That leaves us with 54s squared. So s into 54s squared goes 54s. So that can bring this one down. 126s. That gives us 54s squared plus 54s. Subtract these, 72s. Bring down the 72, and this goes into this plus 72. This gives us 72s plus 72. So when these completely cancel, you know you've done it correctly. So therefore we could rewrite this as s plus 1 into s cubed plus 13s squared plus 54s plus 72. So what we've done now is to take the original transfer function and we've factorised out of it a whole 0 at s plus 1, and then because these two now cancel out, we can do away with them. So that disappears and that disappears. And that now gives us a new transfer function. So we'll assume now that transfer function is observable and controllable, and we'll go on now to design a whole placement control system for that. And that's going to be in the next mini lecture.